Good evening, everyone, and welcome back to tonight's lecture. We're going to continue on where we left off on Tuesday evening. So, tonight we're going to discuss the motions of planets and how that fits into our cosmic perspective. And we're going to end off this lecture with some software demonstration. I want to show you guys for useful things you can use for your scientific and astronomy careers. So before we begin, do you have any questions, any concerns? The floor is open if you want to ask something, want to point something out. Okay, so if there's nothing, let's begin. The planets of our solar system produce no visible light of their own. They are visible only by reflecting sunlight. Mercury, Venus, Mars, Jupiter, and Saturn are all easily visible to the unaided eye and look like stars, but Uranus is usually too faint to be seen and Neptune is never bright enough. So, who of you guys have ever observed some of the planets with your naked eye or through a pair of binoculars or telescope? Yes, Venus is pretty easy. So, what are you guys' favorite planet and why? Why Earth? Why Jupiter? Yes, I will repost the links on ClickUp. So yes, my favorite is Jupiter, and my second favorite is Mars. When I have a chance to take out my telescope, I look at those two planets. So if you were looking down on a solar system from the north celestial pole, you would see the planets moving in the same counterclockwise direction around their orbits, with the planets farthest from the Sun moving the slowest. Seen from Earth, the outer planets move slowly eastward along the ecliptic. In fact, the word planet comes from the Greek word meaning wanderer. Mars moves completely around the ecliptic in slightly more than 2 years, but Saturn, being further from the Sun, takes nearly 30 years. Mercury and Venus also stay near the ecliptic, but they move differently from the other planets. They have orbits inside Earth's orbit, and that means they are never seen far from the Sun in the sky. By tradition, any planet visible in the evening sky is called an evening star, even though planets are not stars. Similarly, any planet visible in the sky shortly before its sunrise is called a morning star. Perhaps the most beautiful is Venus, which can become as bright as magnitude minus 4.7. The cycles of the sky are so impressive that it's not surprising that people have strong feelings about them. Ancient peoples saw the motion of the sun around the ecliptic as a powerful influence on their daily lives, and the motion of the planets along the ecliptic seems similarly meaningful. The ancient superstition of astrology is based on the cycles of the sun and planets around the sky. You have probably heard of the zodiac, a band around the sky extending to about 9 degrees above and below the ecliptic. The signs of the zodiac take the names from the 12 principal constellations along the ecliptic. A horoscope is just a diagram showing the location of the sun, moon, and planets around the ecliptic and their position above or below the horizon for a given date and time. Centuries ago, astrology was an important part of astronomy, but the two are now almost exact opposites. Astronomy is a science that depends on evidence, and astrology is a superstition that survives despite of evidence. The signs of the zodiac are no longer important in astronomy. So in this image we can see where the different astrology symbols and signs is. The seasons. So, before continuing on, do you guys have any more questions about planets and how they move around our solar system? Okay, all good. So before going to the next slide, I want to first have a small discussion and see what you guys' opinion is. Do you think astronomical influences can cause changes on Earth's climate? Can you give an example of why you say yes or why you say no? Okay, so why do you guys think it would? Meteor that passed last year, in fact, meteor that passed this week. Gravity can affect Earth's orbit. That's true. But what do you guys think as well? Solar storms, okay. Any other ideas? That's true, the sun exploded. But what do you think if Earth's orbit would move just a little bit? So say we are, say, about 50 million kilometers closer to the sun or 50 million kilometers further away from the sun. Yes, so we'd be slightly hotter, slightly colder. So if we continue, we will see the seasons are produced by the annual motion of Earth around the sun. But subtle changes in that motion can have dramatic effects on climate. You don't notice these changes during your lifetime, but over thousands of years they can bury continents under glaciers. So, for example, you guys can think about the different ice periods that we went through. And Earth is warmer, and there are no ice sheets even at the poles. Scientists have found evidence of at least four ice ages in Earth's past. One occurred 2.5 billion years ago, but the other three that have been identified have all occurred in the last billion years. Do you all recognize the image in the slide? From which movie it comes from? Come on, you guys have to recognize it. Yes, the day after tomorrow, bingo. So, let's look at the hypotheses of climate cycles. So sometimes a theory or hypothesis is proposed long before scientists can find the critical evidence to test it. That happened in 1920 when engineer meteorologist Milutin Milankovitch proposed what we now know as the Milankovitch hypothesis, and that is that small changes in Earth's orbit precision and in inclination affect Earth's climate and can cause ice ages. So climate cycles, the evidence. So by the middle 1970s, Earth scientists were able to collect the data that Milankovitch had lacked. Oceanographers drilled deep into the seafloor to collect long cores of sediment. In the laboratory, geologists could take samples from different depths, and the cause and determined the age of the samples and the temperature of the oceans when they were deposited on the sea floor. From this, scientists constructed a history of ocean temperatures that convincingly matched the predictions of the Milankovitch hypothesis. The evidence seemed very strong, and by the 1980s, the Milankovitch hypothesis was widely considered the leading hypothesis to explain climate cycles during the current ice age. But science follows a mostly unstated set of rules that holds that our hypothesis must be tested over and over against all available evidence. In 1988, scientists discovered apparently contradictory evidence. So here in this image, we can see in image A, calculations based on the Milankovitch effect can predict temperatures over time. The warming illustrated by the globes shown here took place from 25,000 years to 10,000 years ago and ended the large glaciation. Then in image B, over the last 400,000 years, changes in ocean temperatures measured from fossils found in sediment layers from the seabed matched changes in solar heating predicted by the Milankovitch effect. So, the changeable moon. What can you guys tell me about a moon? Orbit of a planet, orbit of Earth, it has phases. What else can you tell me about it? It's Earth's satellite, it's made of cheese, funny. It reflects sunlight, it's Earth's only natural satellite. Yes, so just a heads up for you guys, your assignment this semester that I will post next week will be about the moon. So yes, it affects the Earth's tides. So just as the planets revolve counterclockwise around the Sun, as seen from the direction of the celestial North Pole, the Moon revolves counterclockwise around Earth. The Moon is about half a degree in angular diameter, and it moves eastward a bit more than half a degree per hour. In 24 hours, it moves 13 degrees. Thus each night you see the Moon about 13 degrees eastward of its location the night before. As the Moon orbits around Earth, its shape changes from night to night in a month-long cycle. Another discussion point. Why do you guys think we only see the one side of the Moon? Yes, it's tidally locked with Earth. That is spot on. Mr. Kutsia, can you, and I'm putting you on the spot, but if you're willing, then can you explain to us what tidally locked means? Otherwise, I will explain it in a moment.
Good day, sir. Can you hear me?
Yes, I can hear you.
Okay, lovely stuff. So what tidal locking is basically, well, the rotation of the Earth sort of matches the rotation of the Moon. So our rate of change when we rotate as a planet, the moon sort of just matches ours. So we only ever see one side because we don't get to notice its change in spin, as far as I
That's
understand.
that's precisely it. Thank you for answering. I really appreciate it.
Thank you, sir.
That's exactly it. So when we continue on to the next slide, the moon always keeps the same side facing Earth, so that is tidally locked. So is everyone comfortable with the principle of tidally locked? Awesome. So the man in the moon that you probably So the man in the moon is produced by the familiar features on the moon's near side, but you never see the far side of the moon. The changing shape of the moon, as it passes through its cycle of phases, is produced by sunlight, illuminating different parts of the side of the moon, as you can see. So when we have the the sun on the left side of this image, as the moon rotates around Earth, only certain parts is lit up by the sun, and that causes the phases of the moon. So notice the difference between the orbital period of the moon around Earth is called the sidereal period, and the length of the lunar phase is the synodic period. So here we can see the 28-day cycle of the moon with all its phases. So here we can see all the stages of the moon. So we will have a new moon. New moon will become the waxing crescent. Then first quarter, waxing gibbons. Full moon, waning gibbous. Third quarter, waning crescent. And then it starts over again. So when you are on Earth, the new moon will be at noon. The first quarter will be at sunset. Full moon will be at midnight. Third quarter will be at sunrise. But what a moon is doing is something you will be learning much about in your upcoming assignment. So you guys are all familiar with a lunar eclipse. I assume all of you have seen a lunar eclipse. So lunar eclipse is not a rare event. It happens quite a few times a year. I will let you guys know when the next lunar eclipse will be. And that is quite pretty to see. So lunar eclipse can occur at full moon if the moon moves through the shadow of the Earth. Because the moon shines only by reflected sunlight, the moon grows dark while it is crossing through the shadow. The umbra is the region of total shadow. If you were drifting in your spacesuit in the umbra of Earth's shadow, the sun would be completely hidden behind Earth, and you would see no portion of the sun's bright disk. If you drifted into the penumbra, however, you would see part of the sun peeking around the edge of Earth. So you would be in partial shadow. In the penumbra, sunlight is dimmed but not extinguished. So here we can see the effects. So right here, that will almost be, that's in the umbra. So what we see here, the reddish part shining on the sides, that's the penumbra. So this is just a better example of how it works. So here we have a light source. Here we have a light source that can be the sun. Here we have our moon, and the screen represents Earth. So here we can see the dark part of the shadow is the umbra, and the light part is the penumbra. Does that make sense to you guys? Awesome. Any questions so far? So putting this into our cosmic perspective, here we can see the Earth, Sun, Moon. So here we can see the penumbra and then the umbra. So why do we have blood moons during some lunar eclipses? So to explain that to you better, we have a few definitions of different moons that can occur. Are you familiar with a few of those moons? Okay, so generally we have a blood moon, a supermoon, a blue moon, and then also sometimes called a pink moon. So last month we had a pink supermoon. So although we wish the names had to do with the color of the moon, they rarely is not quite as mystical and awe-inspiring. So how we name it has nothing to do with the color of the moon. So, sorry, April will be a pink supermoon. So April's full moon often corresponds with the early springtime blooms of a certain wildflower native to eastern North America. And when it blossoms pink, so that's why it's called a pink moon. So the pink supermoon is in some parts of the world also known as the harvest moon. So the term harvest moon refers to the full bright moon that occurs closest to the start of autumn. The name dates from the time before electricity, when farmers depended on the moon's light to harvest their crops late into the night. So the moon's light was particularly important during fall, when harvests are largest. Then we look at a blood moon as based on its red glow. This blood moon occurs during a total lunar eclipse. During a total lunar eclipse, Earth lines up between the moon and the sun. This hides the moon from the sunlight. So when this happens, the only light that reaches the moon's surface is from the edges of Earth's atmosphere. And then the air molecules from the Earth's atmosphere scatter out most of the blue light. The remaining light reflects onto the moon's surface with a red glow, making the moon appear red in the night sky. Then a supermoon appears to us as a larger than usual moon in our night sky. The supermoon looks larger just because it's a bit closer to Earth. Supermoon is actually just a nickname for what astronomers call a perigean full moon, a moon that is full and at its closest point in its orbits around Earth. And when a blue moon occurs, or when someone say once in a blue moon, you know they are talking about something rare. A blue moon is not blue in color. In fact, the blue moon does not look any different than a regular monthly full moon. Rather, a blue moon is special because it is extra moon in a season with 4 full moons. So this usually happens every 2.5 years. Since the 1914s, the term blue moon has also been used for the second full moon in a calendar month. This usually happens only every 2.5 years. Does that make sense to all of you guys? Awesome. So here is some more images of a partial lunar eclipse. And then who of you have seen a solar eclipse? Never. Anyone else? I'll just Google when the next one in South Africa will be visible. But that is really cool to see. I've seen a few in my life before. So from Earth, you can see a phenomenon that is not visible from most planets. It happens because the Sun is about 400 times larger than our Moon, but also on average nearly 400 times further away. So the Sun and Moon have nearly equal angular diameters of about 0.5 degrees. That means the Moon is just the right size to cover the bright disk of the Sun and cause a solar eclipse. If the Moon covers the entire disk of the Sun, you see a total eclipse. If it covers only a part of the Sun, you see a partial eclipse. Uh, yes, Mr. Pitske, partial eclipses actually happens quite often. So, another example, reasoning with numbers. Are you guys ready for this? So the maths in this course is not hard, it's straightforward maths. So in this figure shows the relationship between the linear diameter, angular diameter, and distance of an object. In this case, the Moon, linear diameter is simply the distance between an object's opposite sides. You're referring to linear diameter when you order a 16-inch pizza. The pizza is 16 inches across. The average linear diameter of the Moon is 3,470 kilometers. The angular diameter of an object is the angle formed by the lines extending towards you from opposite edges of the object, meeting at your eye. Clearly, the further away a given object is, the smaller its angular diameter. To find the angular diameter of the Moon, you need to use the small angle formula. It allows you to calculate the angular diameter of any object. Whether it is a pizza or the Moon, this formula is very important in astronomy and you will encounter it used many times in later chapters. So for this example, it is important for us to understand this formula. So angular diameter over 2.06 times 10 to the power 5 angle equals linear diameter over distance. So we are all comfortable with this is the distance, this is the linear diameter, and this angle or distance we see here, this angle here is the angular diameter. So you're all comfortable with these terms. Okay. So in a small angle formula, you must always use the same units for distance and linear diameter. The version of the formula shown here has arc seconds as the unit of the angular diameter. You can use this formula to find any of the three quantities involved: linear diameter, angular diameter, and distance. If you know the other two by cross multiplying. So let's do the example. The Moon's linear diameter is 3,470 kilometers. And its average distance from Earth is 384,000 kilometers. What is its angular diameter? So solution. Because the Moon's linear diameter and distance are both given in the same units, kilometers, you can put them directly into the small angle formula. And now it's as easy as solving for the angular diameter. So the resulting angular diameter is 1,860 arc seconds to 3 digits of precision, which equals 31 arc minutes or about half a degree. So you guys happy with this? Okay. So what happens in a solar eclipse? So in a solar eclipse, the moon moves between the Earth and the Sun, and the moon casts a shadow on Earth. So when we are in the umbra of the moon, that is a total solar eclipse. But when we are in the penumbra of the moon, that is a partial solar eclipse. So let's go back to the previous. Yes, that will always be 2.06 times 10 to the power 5. So just to explain that better to you guys, in the side note we have here, the number 2.06 times 10 to the power 5 in a formula converts the angle units from radians to arc seconds. Pleasure. So here is some nice images of a total solar eclipse. So this is the last slide of this note set before we continue on to the next. So one of my favorite three persons is Bill Nye. Everyone you will meet knows something you don't, and that's always to keep that in mind. So do you guys have any questions about the slides we did on Tuesday and tonight? Anyone else? Anyone else has any questions, any comments? Can we find examples? Yes, there are examples in the textbook. And if you just Google it, you'll find a lot of examples online, a lot of YouTube videos about it as well. So just a heads up for everyone, I will post a notification on ClickUp as well. Next week you will have your first quiz on what we have done this far. So I will open up the quiz on Monday and you will have the entire week to do the quiz. So are solar eclipses only visible from a certain region on Earth? So let's go back a few slides. So it all depends on where the moon and Earth is in their orbits. So in this example right here, we can see the total eclipse, solar eclipse is just as on South America. So it all depends on where the Earth and moon is in their orbits in accordance with the sun, if that makes sense. Yes, a total eclipse was used for that. You are correct, Mr. Groenewald. So now just a little bit more fun part of the lecture and also my bit of preaching. So yes, in the slide we saw, um, South America will see the full solar eclipse, but North America will only see a partial eclipse. So in this set of slides, I'm going to show you a bit of astronomy and science software that you can use every day and should be learning for your careers as scientists or even engineers. Computer scientists, physicists, mathematicians, everyone can use this. So what's astronomy and science software do you guys make use of and do you use on a regular basis? So question, what is the angle of the moon's axis of rotation? That I don't know by heart. That will have to Google to answer. So I've just quickly searched it, and the moon, that's why we only see one side as it is. The moon has a tilt of about 1.5 degrees. So right after this lecture, I'm going to upload the slides because this forms part of Tuesday's slides. It's the same slide set, so I didn't want to spoil anything for you guys scanning it through the slides, so I'll upload it after class. Okay, so coming to the point, have any one of you used any specific astronomy or science software? Yes, Stellarium is pretty cool. So I'm going to show you a demo of the Stellarium in a bit. But some of the software packages that you guys will be using in your careers will be MATLAB. Have anyone one of you guys used MATLAB before? Use Wolfram Alpha. So Wolfram Alpha is a bit based on MATLAB. So in your career somewhere you will meet MATLAB. So MATLAB is a very useful software package to be used for simulations, computer crunching, mathematical models. I use it every day. Unfortunately, it's paid software, but if you know where to look, you can probably find a cracked version, but it's very powerful software to use. Open source version of MATLAB is called Octave. That's basically the same. Yes, so Desmos and GeoGebra, so that's a pretty cool software as well. But for fitting in astronomy purposes, are you guys all familiar with Stellarium? And the rest of the class, is everyone still here or are you guys asleep? So let me give you a short Stellarium demonstration. Do you all see my screen? So in this software, I've got it running from my current location. So right now you can see the sun is setting. We can see in the northeast the moon is coming up. If we move to the west, we can see the sun is setting. We can move around. So here we can see the moon. So in a couple of moments, we will see stars appearing on the software. So if you want to know more about something, you can click on it. So here we can zoom and see the moon, and we get all the information of the moon that we want right now. So if we go down here, we can add our constellation art, and we can see our different constellations at the same time. We can put on our grid, so this is the equatorial grid, or we can put on a azimuth grid. And in here we can also look at, you can activate deep skies object, planets labels. You can even steer your motorized telescope with this software. We can look at exoplanets, we can look at meteor showers, we can look at satellites passing over. So this is some really powerful software that we can use. So if you guys like to play around with software and automation, you can use this to point your telescope to certain objects as well. Yes, this is real time where the moon is currently is and where the sun is currently is. So if you use this in a couple, download it and use in a couple of minutes, you can see real time where everything is. And if you go to the left hand side bar, yeah, you can set your date and time, so you can go into the future, go to the past, say where certain objects will be. Here we can have our sky viewing options. On top we have our location window, search window, configuration window, and in this one right here, the astronomical calculation window is a very cool tool. So if you want to imagine how the night sky would have looked like where certain objects were 2,000 years ago, a million years ago, or 1,000 years into the future, a million years in the future, you plug it in here, and then the software will use the current information that astronomers has done, and it will show you where the objects were and where it will be in the future. So this is some nice cool software you guys can play around with. It's available for all operating systems. It's free software, completely free. So if you guys want to download it and play around with it, I'm going to give you the download link in the chat. And do you know what this logo is or symbol is? Bingo, Linux. Have you guys used Linux before? Familiar with Linux? Who has used it before? So one thing for you guys to, I'm quite impressed with you guys. In last year's class, no one used Linux. Only a few people knew what it is. But for your scientific careers, I would suggest you guys to start getting used to Linux. So if you have a personal computer, I would suggest dual booting it in Windows if you want to use any one Windows. If you Want to use it as your daily driver, then do it as well. You can set up a virtual machine for it as well. So I'm just going to open up connection to my server. Everyone in course 132 has to use Linux, so that is one of your computer science courses, if I'm not mistaken. And a lot of people in the class are computer scientists. So which flavor of Linux are you guys using in COS 132? Ubuntu and Mint, yeah, so those are probably the most common operating systems being used. So right in here now I've opened up a remote desktop session to the server I'm using to do my research on. I'm currently running Ubuntu 18.04 LTS on it. So I'm just going to minimize a few of my things. So this is the basic interface we have of Ubuntu. And it's a very powerful software tool to use. So one thing I really like about Ubuntu is the terminal. So I'm assuming you guys are familiar with the terminal. So what are some of the basic commands that you guys use? Yes, so ls is list directory, cd is change directory, so let's say cd installs, we have clear, we have directory, let's go back. But one thing that is nice about the system, let's go one up directory into the home directory, let's go up one more. Here we can actually see the insides of our operating system. So if we want to do a update, for example, on our operating system, we go sudo. So sudo gives you super privileges. So in Windows terms, that is administrative privileges. You say sudo apt get update. We hit enter. We provide the password, and there it fetches all our updates. So if you want to do upgrades on our software, we can run our upgrade command, and it will upgrade everything we want to use. So I use Linux every day. So for scientific careers, this is something extremely important that you guys should know. And one thing that's also important for you guys is to get comfortable using the terminal, and not, because in Linux you don't have to use graphics. So if you want to use graphics, so I use only what I use graphics for is MATLAB. So this is my MATLAB script I'm busy testing. But to show you what else we can do, can you all see the new terminal window I just opened up? So the server we logged in called this RCH1. So are you all familiar with SSH? So SSH is a communication protocol you can use to log into different machines. Unfortunately, SSH and Telnet is not part of the Windows operating system because this is part of the Unix system, and Linux is based on Unix, Mac is based on Unix, but not Windows. But from Windows 10, Windows has started incorporating these commands. So if we want to log into our server by using the terminal and it's not interested in graphics, we can say SSH-X. So I use X in case we need graphics. Then you can tunnel through the graphics. You have your username at your server address. That can be an IP address or domain name I'm using now. So it's going to ask you for the password for the server. And here we are logged into the server. So now we can say ls. So here we can see our directory. We can go up one more directory and see what's in directory. We can go up one more level, see what's in directory. We can do our updates command, password again, and we can basically do what we want with the system by logging in through SSH. So this is a really important tool for you guys to know and understand. So the sooner you guys get familiar and comfortable by using these systems, the easier it will be in your future careers. So let's do this. Let's go back to our slides. So here we can see some of the most popular flavors of Linux. So right now, currently in the scientific community, the most popular is Ubuntu currently because more software is tested on Ubuntu. And then there's scientific Linux. Have you guys heard about scientific Linux? So scientific Linux was created and developed by CERN for more specifically use at the Large Hadron Collider and to do particle physics on and quantum physics. So it's a standard part of its app store, you can call it, or we call it the app software repository. There are more software available for particle physics and quantum mechanics. But CERN is developed by CERN and Fermilab. So CERN and Fermilab has decided they are only going to support scientific Linux until 2024, and are now starting migrating to CentOS. And then, are you guys familiar with virtualization? So I've seen for your computer science course you run a virtual machine for your operating system. Okay, so what can you tell me about a virtual machine? Yes, you can have Linux on it. It allows you to emulate an operating system. So with a virtualization, you can basically run any operating system as you please without sacrificing your own operating system. So previously, computer hardware wasn't that good, so you can properly do virtualization, speaking about 10 years ago. But now it's become extremely popular method of virtualization. So question, so do you still have to learn about these things? Do you have to know them now? No, you don't have to know them now. This is just something interesting to show you to just prepare yourself for your future careers. So you can, yes, you can do any OS in virtual machines, even the Apple operating system. So this is just something interesting to show you guys. So to show you guys what I mean, I'm going to share my screen again. So can everyone see the rabbit? See the screen I'm sharing? Okay, so let me log in. So this is just my play around virtual machine. So in this virtual machine, I'm using a flavor of Linux developed by System 76 called Pop OS. So Pop OS is a derivative of Ubuntu, and it's specifically designed for to be used with graphics cards. So if you like graphical interfaces and to do a bit of graphics, this operating system is best suited for it. So here I can show you, so you have the same normal terminal that you can use with your normal same commands as always, but now the feature is you can run an operating system on top of operating system. And for example, what we are doing at the Hartbeeshoek Observatory, all of our systems runs Linux. There's not a single Windows system in the entire facility. So what we are starting to do is on our servers, our base server runs the latest version of Ubuntu. And then on top of that, we have a few specific virtual machines that we fire up to use. And you can log into the virtual machines, like the SSH command I showed you. You can SSH into a virtual machine. So when we start doing our research on the virtual machines, so say for example something happens and the machine, something horrible happens, and the machine goes down, then it's easy to continue on because then you can transfer your virtual machine just over to a different machine and continue on as normal. So going back to our slides. So some of the popular virtualization software we can use to create a virtual machine is VirtualBox, that's free to use, KVM, that's free to use. And my personal favorite is VMware. It was a paid version until a year ago, and now it's free for personal use. So I showed you the Ubuntu demonstration. So this is quite true for the scientific community. And then I thought I would end this with Linus Torvalds, the creator of Linux. A computer is like air conditioning. It becomes useless when you open Windows. So that, ladies and gentlemen, is tonight's class. I will upload your lecture slides in the next hour. So if you have no further questions, then you're more than welcome to log off and you have a bit more time to prepare for tomorrow's test. Otherwise, have a great weekend, and I will see you guys in Monday night's class. So do you have a test tomorrow, sir? I haven't scheduled a test for tomorrow. So apparently you have one of your math subjects have a test. So question, are we going to use Linux for this module? No, you're not going to use Linux for this module. This is just the intro to show you where you what tools you need to learn for scientific career in the future. So does the moon's axis still affect Earth in any way? No, it doesn't affect the Earth in really dramatic ways. It's a pleasure. So what is my research in? My research is in an area called spectroscopy. So when you are speaking about emission and emission absorption spectrums from certain objects, I tried to find new and better ways to do spectroscopy to look at the emission and absorption spectrums from celestial objects. Thank you very much, and it's my pleasure. Glad you enjoyed the lecture. Thank you. So spectroscopy is a really cool part of astronomy. And spectroscopy can tell you some really cool details and features from certain objects you're observing. So yes, that is what I want to do for the rest of my life. I want to do research and lecture. Pleasure. So I'm going to stop the recording.